मेरे वाइस ಬರ್ತಾ ಇದೆ ನೋಡಿ ಮ್ಯೂಟ್ ಆಗಲಿಲ್ಲ Good morning. Good morning. So today we are in the 7th class of the series of the strength of material subject. Now till now we have discussed strength of materials unit 1, 2, the stress and strain already we have discussed, and also we are discussing now at present the centroid and the moment of inertia. Now, center of gravity. In the previous class, we have elaborately discussed about the centroid, center of gravity, how to find out the centroid of the given section. Now for regular sections like the triangle or rectangle or square or circle, we are able to find out. We are able to calculate. We are able to know the centroid of the regular figure. Like this is the rectangle. If you join the diagonals, we'll give the centroid. We can locate it very easily. But whereas here it is an irregular section, it is I section, and this is the angle section, L section, and this is the T section. Now all these things are sections are being used in our engineering construction practices. Therefore, we need to understand or locate. We need to understand and locate the centroid of the given sections. Now, while calculating, we should follow certain principles, regulations, rules. So that is because we are all engineers. We should know how to handle or calculate or locate the centroid of the given sections. Now, the main theme of locating the centroid is to where in a column section are being how the loads are in the house loads are being applied. Now, suppose if you apply the force, suppose it is a rectangular column. Now, if you apply the force at the center, the column will resist the force in a better manner. So, suppose if the load is somewhere here, it is other than this area, the centroid, it is understood that there will be some deformation. So, therefore, we need to understand or we need to calculate the centroid. Now, we are in the last class we have discussed about these are the various sections are used in engineering construction practices. Now, this is the channel section, double angle, the reverse there is T section, and this is the circular section. These are all the sections used. And we have calculated the centroid. We have calculated the procedure for calculating the centroid. We have done for all these things. Now, for in the last class we have explained. We have discussed much more about this. How to calculate the centroid for the angle section. Now, different and also for the T section. Locating the centroid, we have calculated. Also, we have calculated the centroid for the same section. And also, we have discussed about to calculate the centroid of an I section. These sections are being used regularly in our engineering practices. And going little ahead, the one moment of inertia. Moment of inertia. We know that the moment means it is rotation. That is bending. Now suppose there is a column or beam. Now the bending moment means no bending moment bending. It is the inertia. Inertia is the force or the against the moment, and inertia force is induced in the material because of its shape. Now, therefore, we need to understand the behavior of the elements, that is load resisting elements, like maybe column, maybe beam. Now we need to understand now how it behaves, and which is the best way to keep the column or to locate the column, to position the column in the right place for resisting the forces. Now, therefore, now we need to understand. Now, strictly speaking, now I'll give one small example. Let us assume that now this is one column. This is one beam section. It is a beam section. It is made out of metal. It is a metal scale. Now, let us assume that it is no beam. Now, for example, if you consider this, now this material has 3 dimensions. Now, one is we have the depth, and we have the width, and also we have the length. There are 3 dimensions we have here in this, isn't it? Now, you may be observed in building construction, in grid construction, and also in the truss work construction. You might have seen. Now, the beams are always placed more depth, and load is applied in this depth. No. So, now, for example, if you consider this as a beam, if you keep the beam and apply the force, there will be a large deformation. Now, suppose if you keep the beam in this position, then the load, the deformation, for the application of the load, the deformation will be less. Now, therefore, see, the material is same material and the section is same, but whereas depending upon the positioning of the material or the element, now the behavior, now that is because of its shape. Therefore, now this moment of inertia, we'll call the geometrical properties of the material. Geometrical properties of the material means that is how it resists, which is the more suitable position of the material to resist the forces. Our object, being an engineer, our object is to minimize the material, quantity of the material. No, that is our object. Therefore, and also, while doing this, while doing all these things, calculating, positioning the columns and beams, we should know which is the. For example, if you keep the column, if you put the column like this, if you apply the force, there will be a deformation, large deformation. Isn't it? Now, suppose if you apply the force in this direction, the deformation will be less. So, therefore, suppose if you go to a site in any construction activity, you can see there are a number of columns which are coming up from the ground level. Now, you can see one column is kept like this, the other column is like this, the other column is different. The positioning of the column, that is is different. Now, depending upon the load acting on the element column. So, therefore, what we need to do, we should understand very precisely how to position the column to resist the forces or the loads. Therefore, we need to understand one thing here. Now, this column material, this column is made out of number of sections. Isn't it? Each section is made out. There are number of sections. Now, rectangular section 1, 2, 3, 4. There are many number of sections made out of, and all these sections are arranged, are fashioned in a particular manner. Isn't it? Now, therefore, these sections are resisting the force according to their positioning. Now, if you keep the material, if you keep the beam like this resists more forces. If you keep the beam like this resists less quantity of force. isn't it? Now, therefore, we need to understand. Now, here, now, let us assume there is a section here. This is one section. There is a section. Now, in this section, now if you cut a section, now if you consider a section, this section has one width, the other one is depth, isn't it? One is B, the other one is D. Breadth and depth. Let us assume that it is a square section. The square section, we have a square section. Therefore, now let us deal with the moment of inertia of the figure. The moment of inertia, that is the behavior of the section. So, for example, this is one section. It is an irregular section. Let it be any kind of shape, any shape. It is a plane area. It is a plane figure. We have considered the section of the beam or section of the column. Now we have considered the section of the column. Now this section. Now, for example, now how it behaves? The behavior of the section about an axis, reference axis. Strictly speaking, about a reference axis. Now, for example, now I have taken this as one section, that is plane figure. I have taken the beam section or a column section. Now, it has the centroid. A centroid. So this centroid. Now I know this is the moment. Now, according to the definition, the moment of inertia of a given figure is about any axis is defined as second moment of the figure about the given axis. Now we can calculate the moment of inertia of this figure with respect to the x-axis. We can calculate the moment of inertia of this figure about the y-axis. We can calculate the moment of inertia of this figure with respect to z-axis. We can calculate the moment of inertia of this figure with respect to this any reference axis. We can calculate the moment of inertia of this figure with respect to this axis. We can calculate the moment of inertia of this reference axis. We can calculate the moment of inertia of this reference axis. In any reference. So it means that with respect to this axis, how the section behaves. How the section behaves. How the section behaves. Now, with respect to this, with respect to this axis, now how this section behaves. Now, therefore, now already I have told you that a beam has a rectangular section. Now, this rectangular section, one rectangular section, two rectangular section, one more rectangular section, another rectangular, like the sections have been arranged in a proper manner. And they are arranged, and it becomes a load of the single element. Either it becomes the beam or it becomes the column. Column has a section and beam also has a section. So therefore, see, now let us understand clearly how to handle, how to deal with this, how to understand how to calculate the inertia force developed by its shape. The shape, now for example, if you go to old houses, old houses means tile roof houses, we can see the rafters in below the tile roof houses. You can observe that the beams are placed. The rafters are placed like this. They have not placed the rafter like this. They have placed because it resists more forces. The tile roof rafters are placed like in like this. The depth will be more and width will be less. Because just example I have given you. Now we will discuss how to deal with this moment of inertia. Now first let us know secondary moment. We are calling this secondary moment. This is the plane figure with respect to this plane figure. Now this is the area of the section. And then this is the centroid. Now we are calculating the moment of inertia of this figure with respect to this axis. With respect to some reference axis. So this reference axis is denoted as AB. AB is the reference axis. Now how to calculate the moment of inertia of the plane given figure. Now this is the given plane figure having the area A with respect to the reference AB. Now this reference is at a distance R from the centroid. Now this reference This reference AB is located from the centroid at a distance r. Therefore, the moment of inertia can be calculated as IAB. IAB is the moment of inertia of this figure about with respect to this axis. This reference. So therefore, moment of inertia of AB is equal to, that is area multiplied by r square. R is the distance. This is the secondary moment. Moment of moment is secondary moment. So therefore, the moment of inertia of this plane figure about AB is equal to area into perpendicular distance square, isn't it? So therefore, similarly, now see if we come now this moment of inertia of the plane figure is equal to area into r square. Area into r square. That is the distance square from there. Unit B is area, distance r into r. Therefore, millimeter to the power of 4. From this equation, so it is r square is equal to I by a. Now just transferring the equation from one side to the other. Now this is r. R is called the radius of gyration. That is understood I by a, radius of gyration. Radius of gyration. Now we should know what is the radius of gyration. Radius of gyration. Now for example, see now this is the axis. Now this is the area plane figure. Now how will it behave with respect to this axis? Suppose if you apply the force, now it rotates like this. Isn't it? Therefore, this is called radius of gyration. Radius of gyration is the movement of the figure with respect to this axis. With respect to this axis, how it behaves. So therefore, it is called radius of gyration. Isn't it? So similarly, now see here, any section you take, any section. Now let us remember. Don't forget that is x-axis and y-axis. So through the centroid of the given figure, isn't it? X-axis and y-axis of the given figure through the centroid. Now these axes are called centroidal axis. These axes are called centroidal axis of the given figure. This is called the centroidal axis of the given figure. Now please remember. Don't forget this. Very carefully listen to these statements. Now, if you understand clearly, definitely you will get around 15-20 marks in the examination. And also, it is essential for civil engineers to keep the column load resisting element in the right position. Now, therefore, you please understand the plane figure, given section, plane figure. Column or beam, column section or beam section, whatever may be. Now, this is the x-axis and y-axis. These are the usually perpendicular axis. This also has another axis in the z-axis. This also has z-axis, another z-axis. The x-axis, y-axis, and z-axis. Now, this is all these axes are mutually perpendicular and they are passing through the centroid of the given section. Centroid of the given section. So therefore, the centroid of the given section. Now, therefore, the mutually perpendicular x-axis, centroidal axis. We are calling all these three axes are centroidal axis. Now, therefore, x-axis, y-axis, and z-axis are mutually perpendicular axis. One should remember this. And now here x-axis, y-y, that is x-axis and y-axis are the two perpendicular axes lying in one plane. Now, for example, this is one plane. In this plane, y-axis and x-axis. This is y-axis and x-axis. That is x-axis and y-axis, and also this has is z-axis. Isn't it? This is z-axis. Now, all these three axes are passing through the centroid. All the three axes, x-axis, y-axis, and z-axis are all the three mutual perpendicular axes are passing through the centroid of the given figure. Centroid of the given figure. The given figure area is A. Isn't it? Given figure A. Now, therefore, let us understand. Now, x-axis and y-y are in the same plane. Z-z is in the perpendicular plane. Isn't it? Now, that means there is x-axis and y-axis. X-axis, y-axis are lying in one plane, and the another perpendicular plane is z-axis. Z-axis will be in the Z plane, isn't it? The perpendicular plane. So x and y plane, x-axis and y-axis are lying in the one plane, and Z-axis is lying in the other plane. So therefore there are and the moment of inertia of this figure, moment of inertia of the given figure, that is figure A, is about x axis is abbreviated as ix. Moment of inertia of the given figure, that is section, maybe rectangle, maybe circular, maybe T section, maybe Z section, whatever may be. Now this is one irregular section. Now this section having the area A, and this is the x-axis. Moment of inertia of the given figure about x-axis is abbreviated as ix. We are abbreviating this as ix. Ix means moment of inertia of the given figure about x-axis. Now similarly, see Iyy, this is another abbreviation used in calculating the moment of inertia. That is the y axis with respect to y axis. Moment of inertia of this figure A about y axis is abbreviated as y axis. So therefore, similarly, with respect to z axis, moment of inertia of this plane figure about the z axis, it is abbreviated as izz. Now, for example, let us assume that there is a column, there is a beam section here. Now, in this beam, if you consider this as a beam, see this, this beam section. Now, there is a section here. One is width. We have width. We have the width. Now, if you assume, let us assume that it is a beam. Now, if it is a beam, this has one width is there, thickness is there, and depth is there. And length is. It is a three-dimensional element, load resisting element. Now this has a centroid. This is the centroid. This has a centroid. This is x-axis. This is y axis, and the other one is z axis. Now z axis. Now let us understand clearly. Now this is the x-axis. The section, how it behaves in the x-axis. Now through x-axis, the section behaves like this. Now because one is section, the other section. There are number of sections are placed. The depth is more. Therefore, this is more rigid in this direction. Therefore, x-axis along the x-axis, the resistance of this beam is more resistant. Now similarly, there is a y-axis. In this y-axis, the width is less. When you apply the force, now what is going to happen? Now this rotates like this, isn't it? In a shorter distance, it rotates. Now that is why if you apply the force, now in this direction, this is less resistance. In this direction, this has more resistance, isn't it? Got it? Now therefore, then see, what is x-axis? More resistant in this direction, it will not rotate. In the y direction, it will rotate. Least resistance. And in the z direction, it is much more resistant because the depth is too much, isn't it? The thickness is too much, therefore more resistant. If you apply the direct force, now definitely it is more resistant. If you apply the force in this direction, least resistant. If you apply the force in this direction, it is much more stronger resistance. Now therefore, the most important thing you should remember here is, we should know that is what is. See, this is section. So this is the section of the beam. Now this behaves along the x-axis. How it behaves? With respect to x-axis. And this is the y-axis. Now with respect to this, how it behaves. Now this is the z-axis. How it behaves with respect to z-axis. So therefore, we need to calculate the moment of inertia of the given figure. Now, how to do it? Let us see. Is it not? Now, moment of inertia, second moment of inertia, whatever the things I have discussed now. Now we will consider the one by one. See the same figure. Now this is with respect to x-axis, y-axis, and z-axis. Now let us consider a plane figure. A plane figure is considered. We have to consider a plane figure. Now it is a plane figure having the area A. The centroid of the given figure. This is the centroid of the given figure. Now this centroid lies at a distance x from y-axis. The centroid of the given figure lies at this distance x from y-axis. Now similarly, the centroid of the given figure lies at a distance y from the x-axis. And similarly, now this is the z-axis. Now with respect to this, now this is the z distance. The z-axis is lying at a distance z from the centroid of the given figure. Now therefore, now with respect to this, now the moment of inertia of the given section about x-axis. Now this is x-axis. This is y-axis. We are calling this as y-axis. Y-axis is the moment of inertia of the given figure. This figure about x-axis. Now therefore, that is equal to area multiplied by distance square. So that is what we have written here. Area I-x-x is equal to I-x-x, moment of inertia of the given this figure about x-axis. Moment of inertia of this figure about x-axis is equal to area into area of this figure into distance square. Therefore, this is what is filtered here. And similarly, this is the moment of inertia of the given figure about y-axis. About y-axis is equal to I-y-y, and this is area into distance square. Area into distance square. And similarly, now this is the z. Now this is the z axis. This is the z axis from here to here. The z distance. This is the z distance. The moment of inertia of this figure with respect to z axis. Now that is written here. It is I z. And please understand, the unit is moment of millimeter to the power 4, because area is in millimeter square. Z is the distance. So z square, therefore millimeter square. Millimeter square into millimeter square is millimeter to the power of 4. Millimeter to the power of 4. Now please remember, always the moment of inertia will be calculated with respect to some reference axis. With respect to reference axis. Now this is x-axis. X-axis, I-x-x is equal to moment of inertia of the figure about x-axis is equal to, that is area into distance square. Moment of inertia of the y-axis, moment of inertia of the given figure about y-axis is equal to area of the figure into distance square. Now similarly, moment of inertia of the given figure about z-axis. This is the z-axis. This is the z-axis. Z-axis distance, isn't it? Area into distance square, that is I-z, isn't it? I-z is equal to area into distance square. This is how we can calculate the moment of inertia of the given figure, isn't it? Now let us see. Now please understand here. Now see, it means exactly the meaning of this. No, the section. No, this section. The section. No, this section. How it behaves with respect to this x-axis. Suppose if you apply the force, now how it behaves. The behavior of the material. It rotates like this, isn't it? With respect to this axis, how the material behaves. Isn't it? The section how rotates, isn't it? Now similarly, with respect to this axis, how it behaves. The behavior of the section, isn't it? Now therefore, in which direction the material section behaves with respect to the application of the load. That is how we can decide which is the right place or right positioning of the columns of these. Now, perpendicular axis theorem. In the perpendicular, now this is one theorem that is easy to calculate the moment of inertia through along the axis. Which axis is the best? And now we should know where now we are discussing x-axis, y-axis, I-x-axis, I-y-y, I-z. But which is the more relevant to our load resisting here, our element, which is the more relevant position to resist the given force. Therefore, everything it should be quantified. We have to calculate in terms of some mathematical relations. No, what is how do you know? How do you calculate? What is the quantity what is the resistance induced in the material due to its shape. Therefore, now what there are two theorems here. One is perpendicular axis theorem, the other one is parallel axis theorem. Now let us understand one by one carefully. Now, perpendicular axis theorem. Perpendicular. The statement. What the no see. Now this is the given section of the figure. You consider, let us consider a whatever may be the section, maybe circular, maybe square, maybe rectangle, maybe T section, maybe I section, whatever may be the cross section of the load resisting element. Now see, now this is the centroid. We know how to calculate the centroid. Sigma AX divided by sigma A, calculate, and we will get the centroid. It is possible we can calculate the centroid. Now after calculating the centroid, now these are the x axis and this is the y axis. Now these and also there is a z axis. Isn't it? Now therefore, now please understand x, y and z are the three mutually perpendicular axes passing through the centroid of the given figure. Passing through the centroid of the z axis, x axis, y axis. All these three axes are passing through the centroid. Isn't it? Now therefore, these axes are called centroidal axis. These axes are called centroidal axis. Centroidal x axis, centroidal y axis, centroidal z axis of the given figure. Given figure, area A. Isn't it? Now please note that is, once again I will tell you, that is x axis, y axis and z are the three mutually perpendicular axes passing through the centroid. Now these three axes are called centroidal axis. These three axes are called centroidal axis of the given figure. Now see what perpendicular axis theorem says. Let us see what perpendicular axis says. The perpendicular axis theorem says that statement. There is a statement. The statement is like this. See, x, y and z are three mutually perpendicular axes passing through the centroid. X, y and z are the three mutually perpendicular axes passing through the centroid. Then Ix, Iyy and Izz are the moment of inertia along x axis, y axis and z axis of the given figure area A. Then moment of inertia of the given figure about z axis is equal to moment of inertia about x axis plus moment of inertia of the figure about y axis. Isn't it? This is the statement. The statement, what the statement says, x, y and z are three mutually perpendicular axes passing through the centroid of the given figure. And Ix is the moment of inertia of the figure, Iyy is the moment of inertia of the figure, Z is the moment of inertia of the figure about the centroidal axis. Then Ix, Izz, moment of inertia of the z axis is equal to moment of inertia of about x axis plus moment of inertia of y axis. Now this is the statement. Now normally this will be asked in the examination. Normally either perpendicular axis theorem or one of them will be appears normally in the examination. So it may carry 5 marks for your examination. Now this is the statement, very simple statement, very simple. And first you have to let us understand what is the figure and what is the centroid and what is which is the x-axis, which is the y-axis and which is the z-axis, and how to I-axis is what, Iyy is what, and Izz is what. Now let us understand very clearly, isn't it? Now we want to prove this. Now we need to prove this, isn't it? Now this is a statement according to perpendicular axis theorem. This is a statement according to perpendicular axis theorem. Now we have to prove this. Izz is equal to Ix plus Iy. Now let us see how to prove it. Now let us see how to prove that, isn't it? Now consider an elemental strip. Now this is the area of the figure. Now we will consider a small area, elemental area, delta A area. Now this is the whole entire figure area is A, and this is the delta A is the small elemental figure. We have considered this elemental figure, elemental area lies at a distance, lying at a distance x from y axis and y from x axis and z from z axis. Now this is the figure, given figure area.